Now let's talk about electrical resistance. Electrical resistance is how hard it is for current to flow. This will finally let us put some numbers on that weird sliding scale between conductors and insulators. A conductor is a material with very low resistance. That means it's very easy for the electrons to move around and the current to flow. An insulator is a material with a very high resistance. That means it's incredibly hard for the current to flow. The electrons only move slowly. This doesn't, of course, mean that they don't move at all or that it's impossible for the current to flow. It just takes a long time to get from here to there, and that's why insulators do such a good job of insulating. Resistance is measured in ohms, where 1 ohm of resistance is 1 volt of voltage difference per ampere of current. To visualize where resistance comes from and why certain materials have more resistance than others, let's look at crowd control. This is what it looks like to an electron on the inside of the circuit. Here are all the other electrons, and here is you trying to get through. Under what circumstances would be easier to get through? And don't say a less crowded street, because metal wires and ceramics are solids. You're not going to get fewer electrons by saying, oh, I think I would like my wires to be made of gas today. If you're trying to get to the pharmacy or the grocery store or the bank, and that is here, under what circumstances would you get there faster? Think about ways you could change the geometry of the street, press pause, develop a few hypotheses, and then press play to check your work. Well, first and foremost, there's the material. Copper is a good conductor. Silver is a better conductor. Gold is the best conductor there is. That's why high-grade electronics are so expensive. Their circuit boards are plated with gold. Write those 3 things down. Copper's got a low resistance, silver's got a lower resistance, and gold's got an even lower resistance than that. If you want to modulate the resistance, you'll use certain types of ceramic and put them in a little case, and you will have a resistor. A resistor is something that's designed to have a specific resistance, and how much resistance will depend first on the material that's inside this little painted case, and next on the rest of the answers to this question. After the material, what else could you change? Well, let me tell you, if your grocery store or bank or pharmacy were right here, you could get there a lot quicker, wouldn't you? You're practically there. The second thing resistance depends on is length. Short wires, short lengths, have lower resistors than long wires. Think about it. It's going to be a lot harder to get all the way down to here. That's your second point. The third thing that resistance depends on is width. If this street were 6 times as wide, you may have the same number of people, you may have even more people, but you'd have opportunities to dodge and twist. It's those narrow little streets, the ones in Boston that used to be cow paths, the ones in Jerusalem for when 1 donkey was considered the height of modern transportation. Those are the ones that's really difficult to get through. Wide widths have lower resistance. Narrow wires, and by narrow we mean the diameter of the wire. Really, it's the cross-sectional area. But the narrower the wire, the higher resistance. The last variable in an object's resistance is its temperature. Temperature has to do with average molecular kinetic energy. The warmer a solid is, the faster its molecules are in motion. Get it warm enough, be bouncing so crazily that you can't keep them within the walls of a cubicle container. That is to say, the solid will melt. Get them warm enough again, and you won't be able to keep them flat on the tabletop or in the bottle. That is to say, the liquid will boil or vaporize. Now, consider yourself as the babysitter or GON leader or groups leader for a group of 30 preschoolers. You want to get them to go in for ein Kelohenu. Yes, yes, you've applied a voltage difference. You're holding up the sour worms and the sugar. Come this way, children, come this way. There will be candy if you cooperate. How easy is it going to get all 30 little preschoolers to move in the direction that you want to, given that it's just you? Well, let's see. How about if it's 8 in the morning, they're all well fed and they're all really, really tired. You hold up the sugar and say, here, Yeladim, this way. They're not all that energetic, honestly. Probably they'll see the candy and they'll walk toward you. Let's try this again. It's 11:59 a.m. They are completely zazzled up on sugar already, and they've been inside all morning long because it's Shabbat, Rosh Chodesh, Hanukkah, and there are 3 Torah scrolls. Even if you have the candy in your hand to provide at least 1 plastic bag's worth of voltage difference, how easy is it going to be to get all 30 of those preschoolers to move in the direction you want to? Are you kidding? They'll be bouncing off the walls. Yes, they'll all be moving. They'll all be moving more. They'll be running around screaming, jumping on the furniture, climbing the walls, trying to get out the window, punching each other, grabbing each other's toys, but they won't all be moving in the right direction. Resistance and temperature works the same way. Cooler materials have a lower resistance. It's easier to get them to go in the direction that you want it to go, at least electron by electron. Hotter materials have a higher resistance. This is one of the reasons that overheating materials in a circuit is a problem. It changes the resistance, which changes the electrical current.